who are working on computational studies. Computational studies is a very, very useful and valuable science. Do it. But when you do something, you must in your mind think that what does it mean physically? If you are just changing the parameter in a computer program and you are publishing it, then you can be a good typewriter, you can be a good computational teacher, but you cannot be a scientist when you can't bring it to the physical world, which you can't visualize. So whatever you see, you must explain it logically. And if you are not able to explain it not logically, I will never appoint you as a lecturer because of your 100 publication in that field. Because you can be a good computer operator, but if the logic is there, then you are really a great scientist. Scientific argument is there. Why this result comes? Explain this to me. If you can do that, you are a scientist. Otherwise, you can be a technician or a computer operator, which is also a good thing. I am not belittling it, but you shouldn't expect a scientific level for that, right? So whatever you do logically. Whatever you say, speak the truth. And in particular, as a teacher, if you don't speak the truth, your student will tomorrow know 200% more than you, and they will laugh at you. Because the world is very quickly changing. The facilities are very quickly enhancing. The resolution is very quickly changing. And the people who couldn't see a micron level crystal can now see a few angstrom size crystal very easily, even in Peshawar. I'm not talking of the developed world. In your own country, you can see it. So work hard, become talented, and I'm telling you again and again that if you are appearing in an exam, in a competition, and your marks are 99 and another person get 100, the 100 one is passed and you are failed with the 99% marks. And that takes the train of knowledge forward, that everybody is struggling hard, and that hard struggle results in the innovation, in the inventions, and in the development of the world. Thank you very much for today. Any question?
You told that remind me about itching.
Itching. Yeah, it's very interesting. So he was not among the students and he remembered that. It is very unfortunate. Itching, crystal is a different phase in a glassy matrix. Listen to this very carefully. Crystal is a different phase in a glassy phase. One phase will be more reactive, one phase will be more reactive to a chemical, for example acid, in comparison to the other. Crystal is a different phase in a different matrix. The matrix and the crystal reactivity will be different towards an acid medium. Let me say that you have a ball of clay mixed with small stones. and you want to see the small stones, how will you do it? To remove the clay from the face of the stone. Clay and the stone, they will react differently to water. So shake this ball in water for some time, the softer material will erode and the harder material will be left. So what will you see when you shake it in water? These will appear and the crystal will appear and the mud, the clay will be washed away. So when you have a glassy medium and there is crystal inside it, the glass is softer than the crystal, then you put an acid upon it, right? This is a beaker of acid. You put the sample here for 5 seconds, for 2 seconds, for 1 second, for 50 seconds, depending on the hardness of the material. And when you take it out, sometimes only the fumes of the acids are enough. That washes away the surface and you see the crystal phases because one is less reactive in comparison to the other. That is called chemical etching. But if it is the same phase throughout, if it is the same phase throughout, this means that all are crystals, but it appears like this. How will you see the grain? To see the grain, you have sintered this material, for example, at 1500 degrees C, and it appears like this. So what you do? 10% of this, how much is 10% of this? 150. 1500 minus 150. It will be 5, 4, 3, 1350. Heat it for 10 minutes or 20 minutes at 1350 and cool it. What will happen? These boundaries, the crystals with a little bit shrink or relax, and that relaxation will give you the grain boundaries. So you will be able to see the grain size. So this is the etching mechanism, and it is called thermal etching. Chemical etching, thermal etching, and you have to select a particular acid that it doesn't damage you, it doesn't damage your sample. Sometimes fumes of the acid are enough. I have done etching for samples. So if it is, for example, 5% acid solution, aqueous solution of hydrochloric acid, and I hold the sample in freezer with mouth and everything completely covered. Then in 5 seconds, a material wash away the surface and I can see the crystal. Sometimes I throw the sample into it and put it there for 2 minutes, 3 minutes, 5 minutes. So it is trial and error, and it depends upon your experience that how much exposure to the acid is enough for your sample to etch, right? And you can easily resolve the different phases inside the material. So if you look into this wall, you polish it, you will not see the minor features in it in a systematic manner. But if you etch it with something, then you will see the minor stones inside it. And etching is a very frequently used technique to see the small crystals or large crystals in materials and different phases. Thermal etching and chemical etching. It is needed for scanning electron microscope and for optical microscope in Transmission electron microscope, you don't need UV etching, because in that you can transmit the electron beam through the crystals. The sample is very thin, but there are chemical routes of thinning as well. And what I tell my students frequently, that I worked for 15 or more than 15 years from morning to evening on different electron microscopes, some of the world very good electron microscopes, but my knowledge is not a primary school level knowledge in that discipline. So this means that the knowledge is a very broad field. Every technique has many books written upon it, and what we tell you is just our exposure which we are reflecting in our lectures. This never means that this is the full explanation of the subject. One thing which I usually tell the students, that if you ask me what is an electron microscope or what is a microscope, and I answer you that it is a technique to resolve features or to see things which are inaccessible to the naked eyes, I am a very intelligent teacher, because I told you the easiest definition that could be. But if I told you that I don't know, go to the library and there is a book on electron microscopy and look into it. The book will have at least 10 chapters, and at the end of every chapter there will be 20 to 30 references. So this means that I open to you a door of the full world of microscopy. So if a teacher doesn't abruptly answer you and show you a direction, it will be much better for you to see the things in more details. There may be, I don't know the exact definition. So instead of telling you a wrong definition, why shouldn't I send to the library? Because if you are a primary level student, then I should try my best to convince you. But if you are a PhD or MPhil or master level student, then it is better for you to go to the library. And if you don't understand something, then come to the teacher and ask him. Right? The more you read, the more you learn. The diverse opinion, I, for example, read 5 books of quantum mechanics, and I couldn't understand quantum mechanics in the 4 books, but the 5th book convinced me what I was looking for. So the more you read, the more opportunities you find for your satisfaction and for your knowledge. Any question, please?
I just say the role of polarization. What's the temperature affects polarization of
Of course, temperature controls the phase transformation. One phase will be easily polarizable in comparison to the other. Secondly, when you polarize sample in a hotter environment than a cooler, again, you give some kinetic freedom. Because we applied an electric field, and if the poles, the dipoles reorient themselves easily, obviously the polarization will increase. And if they can't reorient themselves easily, if you look into the soft magnetic materials, their hysteresis loops appears like this. If this is the hysteresis loop, it appears like this. What does this mean? That this field was like this, but the coercivity decreased from 5 ampere per meter, for example, to 1. So it became a thin line, right? This thin line means it is a soft material. If the hysteresis loop is like this means it has a big coercivity, and big coercivity means that the material cannot be polarized and depolarized. The domain's orientation, if they are magnetic, if they are electric, they cannot be interchanged easily. When it is difficult to reorient the magnetic domains, we see the material is a hard magnet. If they can be easily reoriented, we call it a soft magnet. Yes. When you ask me, then I can tell you. If you don't ask me, I don't know then.
Then you get up. Nano glasses.
Nano,
Nano glasses.
nano glasses. I don't know anything about nano glasses because when I was talking about the soft magnetic materials. Soft magnetic materials are such material where it is an amorphous material. Soft magnetic alloys are amorphous materials, but you crystallize them at nanoscale. When you crystallize them at nanoscale, you introduce nanoscale domains inside them, magnetic domains, and they make them soft magnetic alloys. So, if I have no experience of nano glasses, but take, you can, you can crystallize glasses at nanoscale and they will become glass ceramics, right? But nano glasses, I have never heard that term or name in the books I have read up to now.
Is it possible to define the term quenching?
What?
The term quenching.
Quenching.
Yes.
Yeah?
In DDF law.
In?
DDF law. In DDF, is it possible to define the term quenching? If we define the term annealing, capturing, and ionization?
From DTA plot, you get the optimum crystallization temperature. Regarding quenching, I am explaining this. From the DTA plant, you get the optimum crystallization temperature. The optimum crystallization temperature is not the optimum sintering temperature. The optimum crystallization temperature, crystallize your material at that temperature very quickly and optimally. But it never means that it is the optimum sintering temperature. The crystallization temperature is associated with the crystallizability of the material at that temperature. Sintering temperature is associated with the densification of the material. So there are two different temperatures. One is crystallizing the material, the other is densifying the material. And in thermal etching, you are just relaxing the grains. You are just relaxing the grain. This cloth is spread here and there are minor features here and I just a little bit move them. And this small movements just resolves the intergrain boundaries. So when I heat the material, it expands. When it cools down, the boundaries slightly move. It is like this, these fingers, and they become a little bit like this. So it has things to do with the thermal expansion coefficient and with the densification of the material. So the DTA, I think, cannot tell you about the quenching temperature, but the optimum sintering temperature, 10% less than that, can usually help you if you heat treat the material for 10 minutes or 20 minutes there. But good scientists in the old times, people used to say heat it there for 20 minutes. And then after some days, a good scientist told me, why are you heating it for 20 minutes? 10 minutes is enough because you want to take the material to that level and then cool it, just to relax the grains. You are not using that material for application. You are just heating and cooling the material to resolve the grains inside the material. Yes. No question? Thank you very much.